Hello there, this is Truth Socrates. Welcome to today's video on infinite series. And today we are going to take a little pause from all those tests for convergence or divergence that we have been talking about in the last few videos. We did the divergence test, integral test, ordinary comparison test, limit comparison test, and alternating series test. There's still two tests that we are going to talk about, but they will come after this video. In today's video, we are going to talk about two different kinds of convergence. So some series are what are called absolutely convergent series, and other series are called conditionally convergent series. So from the name, both of these kinds of series are convergent, but if you were to pick which one is more special, I would say that absolutely convergent are the superior kind of convergent series. So we are going to begin by reviewing some of the definitions that we have seen in earlier videos. So what I have done is I have gone through some of the previous sections, and I've literally cut and pasted the important definitions that we have seen there. This is found at the bottom of the PDF that accompanies this video. And let's begin by reviewing the definition of the limit of a convergent sequence. Okay, because everything goes back to sequences. We say that an infinite sequence a sub n, let's just say n going from 0 to infinity, converges to a limit L if for every positive number epsilon, no matter how small, we can find a positive number n such that if the subscript n is bigger than capital N, then the term a sub n minus the limit L in absolute value is less than epsilon. So we write this limit symbolically as limit as n goes to infinity, a sub n equals L, or we use the symbol an right arrow L, which we pronounce as an converges to L or an approaches L. So we also say that the sequence an from 0 to infinity is a convergent sequence, and we call y equals L, the horizontal line, as the horizontal asymptote for the sequence. So from this definition, we started talking about infinite series. Okay, so in the notation for infinite series, we have summation n equals 0 to infinity a sub n. And a sub n, of course, are like the terms that we saw in the last definition. These are the terms of our infinite series. From the infinite series, we form the partial sums s sub n. So by definition, they are the summation k equals 0 to n of a sub k. And maybe let's remind you that it is a sub 0 plus a sub 1 and so on, plus up to a sub n. Okay, I will clean that up later. Okay, so from the infinite series, we form a new sequence, a sequence of partial sums, S0, S1, S2. I hope you remember this. You made a spreadsheet where we had the terms of the sequence and the partial sums up to a sub n. All right, now that we have this new sequence of partial sums, we can talk about what happens to them. There are four possibilities. The sequence of partial sums converges to a limit s, in which case we say that the infinite series converges and the exact sum of the infinite series is equal to this number s. Sometimes it's possible to find the exact sum s, sometimes it's impossible. So it is often kind of like a consolation prize that we find out whether an infinite series converges or not. That's what we did with the 5 tests for convergence or divergence. So the other three possibilities are all bad, undesirable, if you will. The sequence of partial sums diverges to infinity, meaning they just keep getting bigger and bigger unboundedly. Or in the exact opposite direction, the sequence of partial sums diverges to negative infinity. Or, and we saw that this could happen for geometric series where the common ratio is negative, the partial sums don't fall into any of the three categories above, does not get closer and closer to a limit s. The partial sums don't get bigger and bigger, or more negative as we add more terms, in which case we say simply that the infinite series diverges. Okay, so these are, of course, completely useless series, at least for 2 and 3. We can say that the partial sums get bigger and bigger. Okay, the fourth kind are just crazy series. Okay, so at this point, we're ready to talk about the two concepts of absolute convergence and conditional convergence. All right, here we go. So this is essentially in one screen. You see the most important concepts from this video. First definition, absolute convergence. A series, summation n equals k to infinity of a sub n, is absolutely convergent, or we also say converges absolutely, if the series that we get by forming the infinite series with the absolute value of the a sub n's, that new series converges. Converges in the sense of our previous definitions. Conditional convergence. A series is said to be conditionally convergent or converges conditionally if the series formed using the absolute values of the terms, like we did in this first definition, diverges to infinity. So it's the opposite of converges, and it better be diverges to infinity because all of the terms are positive once you take the absolute value. However, the original series, where we just do summation n equals k to infinity of a sub n, still converges. Okay? So in other words, we have a conditionally convergent series. If you have a convergent series, you start off with a convergent series, but once you make all the terms positive, right, by taking the absolute values of all of the terms, forming that new series, that new series diverges. All right. The important thing to know is that if your series with the absolute value converges, in other words, if your series is absolutely convergent, then the original series also converges. Okay, that kind of makes sense, right? Why would you bother taking the absolute values, have that converge? Oh, and then, but you know what? The original one, oh, it's bad. Don't go there. It diverges. Okay, so if it so happens that once you take all the absolute values of the terms, that new series converges, then the series that you started out with also had to converge. All right, now that we have had that review, we can take a look at some examples. We will be covering basically section 2H of our textbook and little bits and pieces of sections 2I and 2J. Not a whole lot. All right, so I, again, literally cut and pasted some examples from our previous videos. So we saw in the alternating series test, the alternating harmonic series. So remember how it works. You take the absolute value of the terms. Ooh, sounds familiar. In this case, that would be just 1 over n, ignoring the minus 1 to the n plus 1. And you ask, are these terms approaching 0? And are they decreasing? Okay, so 1 over n is obviously getting closer and closer to 0 and decreasing. So, end of story. According to the alternating series test, this alternating harmonic series converges. Okay, so we also said that it doesn't have to be just minus 1 to the n plus 1 over n. We can put a power over that n. Okay, so it's an alternating P series. And does it matter if it's 1 over n or 1 over n to the p? Yeah, if p is positive, that will still go to 0, and it's still decreasing. As n increases, n to the p increases, 1 over n to the p also increases. Okay, so therefore, the alternating p series also converge according to the AST. All right, so let's talk about absolute and conditional convergence. Right? We are starting with a converging series. So now let's ask, is the series formed by taking the absolute value of the terms going to be convergent or divergent? Okay, so test for absolute convergence. So instead of this series, we are going to put absolute values around them. Okay, I had to go backstage and grab some absolute value bars. So we are going to take our terms and we will put them inside absolute values like that. And of course, when we take the absolute value of those terms, the minus 1 to the n plus 1 just goes away. Didn't we just say that? Yeah, we just said that. So therefore, this is going to be just summation 1 over n. Okay? Take note though, we are not doing the alternating series test. We already did that, right? We are doing something else. We are asking if our original series with a minus 1 to the n plus 1 over n is absolutely convergent, okay? So we will take the absolute value of the terms, and then we're going to ask, are you convergent or divergent, okay? But this is the original harmonic series. And of course, we know that it diverges, okay? So the original series converges, but the series with absolute values diverges. So therefore, we are not absolutely convergent in this case. We are only conditionally convergent, okay? So thus, by definition, the alternating harmonic series is only conditionally convergent. Okay, so let's stay with alternating P series though, and let's manufacture a couple of other examples. I believe we may have talked about something like n to the 7 over 5. In one of our earlier videos when we did the integral test, we talked about P series, and if your P is 7 over 5, that's bigger than 1. The P series, where the numerator is 1, we know converges, okay? So with that in mind, consider next this alternating P series. So again, this alternating P series is convergent by the AST. All of them are. It doesn't matter whether you put 7 over 5 or 1 or 5 over 7, which is what we're going to do in a little bit. Why don't I make a copy now? Okay, so let's put that over here. Okay, so again, test for absolute convergence. Okay, we're going to take the series and we're going to put the terms inside absolute value bars. Okay, so we're going to take that and put them inside. All right, but once again, when you take the absolute values, the minus 1 to the n plus 1 just goes away. Okay, so with absolute values, we just simply get 1 over n to the 7/5, and we set, which is a P series with P equal to 7 over 5, which is bigger than 1. And so we know this converges by the integral test, okay, which allowed us to conclude that the p-series with p bigger than 1 converge, those with p less than or equal to 1 diverge. Okay, so thus, by definition, this alternating p-series is absolutely convergent. Okay, so finally, let's look at this p-series where we are going to flip the 7 over 5, turn it into a 5 over 7. Okay, so finally, consider this infinite series. Okay, so again, one more time, this alternating p-series converges. Test for absolute convergence. So we're going to take the infinite series and we're going to put the absolute values around our terms. So get in there. There you are in the prism of absolute values. And of course, just like our last two examples, it just means that we have 1 in the numerator. There you go. However, this time the p is smaller than 1. It's between 0 and 1. And we know that this kind of p-series diverges, which is a divergent p-series. So thus, just like the harmonic, the alternating harmonic series, this alternating p-series, there you go, is only conditionally convergent. Okay, so shall we recap from the top? We have the alternating harmonic series, and when we took the absolute values, that ordinary original harmonic series diverges. So this series is only conditionally convergent. Shall we make this all caps so that you can see exactly what it says? Convergent. Okay, so next we changed the exponent to 7 over 5. And this time when you take the absolute values, that p-series converges. So therefore, this alternating p-series is absolutely convergent. All right, and finally, we changed the 7 over 5 to 5 over 7, which is smaller than 1. So when we took the absolute values, we got a divergent p-series. And therefore, this alternating p-series is only conditionally convergent. Okay, so one of the things that hopefully you picked up on is that if you start out with the series which we know already diverges, yeah, don't bother. It's pointless to test the absolute values. As we're about to see, if the absolute values, the series with the absolute values converges, then your original series also converges. So if it diverges, don't bother. It's garbage. Throw it away. We're going to go to our PDF. All right, so I started the section in the PDF talking about a sequence that we saw in section 1b, where we looked at sine of n from 0 to infinity. Okay, so here's the sine function, the sine wave, 0, pi over 2, pi, 3 pi over 2, 2 pi, and so on. But our sequence is sine of n. So basically it means we want sine of 1, which is over there, sine of 2, which is over there, sine of 3, close to 0, sine of 4, not so close to 0, sine of 5 rather, close to -1, but no cigar, and so on. Yeah, we will never be equal to pi or 3 pi over 2 or any multiple of pi, because that would mean that pi is a rational number. And it is a famous, not very simple result of mathematics that pi is an irrational number. In fact, it's transcendental, even worse than being just irrational. Okay? But furthermore, as we can see from the way it's behaving, well, sine is sometimes positive, sometimes negative, sometimes close to -1, sometimes close to +1. Okay? So the sequence sine of n simply diverges. Yeah, the limit does not exist. So according to the test for divergence, if you look at the infinite series made of sine n, forget it. That is automatically divergent. Okay, but now, let's see what happens if you have sine of n over n squared. Okay, so we are going to take these numbers, these values, and then we'll divide by n squared. Okay, so we'll get like this number divided by 4, this number divided by 9, this number divided by 64, and so on. Okay, so that is not an alternating series. It is sometimes positive, it is sometimes negative, but we do know something about sine, and that is it's always between -1 and +1. Okay, so therefore, this series that we have, sine of n over n squared, oh, by the way, I guess we should start at 1. Yeah, not 0, but 1. It's going to be between 1 over n squared and -1 over n squared. Okay? Does it mean that, let's think about the divergence test, which we said applies to the series of just sine n because the terms don't go to 0. But wait a minute, this time 1 over n squared goes to 0, -1 over n squared also goes to 0. Oops, we're out of luck. By the squeeze theorem, the series, the terms of the series goes to 0. And once again, if the terms go to 0, the divergence test does not give you any conclusion. It is inconclusive. We need to try something else. All right, and this is where the key property, one of the key properties of an absolutely convergent series is going to be very useful. If the series with absolute values on an converges, turn all of them positive, then the original series, summation of an, without the absolute values, also converges. So in other words, if you can show this very high bar that when you turn all the terms positive and you get a convergent series, then the series that you started out with also had to be convergent. Okay, so the way to do this is to cleverly, ingeniously take advantage of the ordinary comparison test. By now, maybe you've become a fan of the limit comparison test because it's so fancy. This one, the ordinary comparison test, rescues us. All right, so here's a little warm-up. Okay, we have two inequalities involving 5 and -5. They're both true, aren't they? 5 is bigger than -5 and less than or equal to itself, 5. Similarly, -5 is at least -5 and definitely less than or equal to +5. Okay? All right, so now, what do 5 and -5 have in common? Oh, of course, they have the same absolute value. Duh! So, how can we put together these two compound inequalities into a single compound inequality? In the middle, we have either 5 or -5. So we'll put plus or minus 5 in the middle. Okay, on the right we always have 5. Okay, but so if we had -5 over here, we want to turn it into +5. And of course, the best way to do that, simplest way to do that, is to take the absolute value. Okay, similarly, on the left of both compound inequalities, we have -5. So the simplest way to do that, and it looks slightly complicated, no, it's just 2 steps. First, you take the absolute value of plus or minus 5. So now you get +5. And then you take the negative, the opposite of that absolute value. So that way you will always get -5. All right. So why is this silly warm-up important? Well, it's because we're going to use it on the terms of our sequence. Ooh. If you have a term, a sub n, it could be positive or negative. But if you take the absolute value, like we did over here, you will get something which is definitely bigger or equal to the original term. Similarly, if you take the absolute value, but then put the negative in front, you'll get something which is smaller than the original term. Okay, so now here's the magic. Remember that we can use the ordinary comparison test only on series with positive terms. They don't work on alternating series. They don't work on series where sometimes the terms are negative. Okay, so what we're going to do is we are going to add absolute value of n to all 3 parts of this inequality. Watch. So there we go. Add absolute value of n on the left, a sub n. Add absolute value of a sub n in the middle, and on the right. Okay? But how does it simplify? Well, these two are simply going to cancel each other. This one, nah, they don't quite simplify. This one, ooh, those are the same. So they double. Aha. So the middle part, which looks a little awkward, it's okay. an plus absolute value of an is at least 0. It's not negative. And less than or equal to twice the absolute value of a sub n. Okay. So let's give them a name. Let's give this sum, a sub n plus absolute value of a sub n, the name b sub n. Okay, so this inequality says 0 less than or equal to b sub n less than or equal to twice absolute value of a sub n. Okay, but what are we told in the theorem? We're told that the summation, the series where we have absolute value of a sub n, that converges. All right, so if we look at the series where we have absolute value, if we have twice absolute value of a sub n, then that series also converges. All right, so check it out. B sub n is smaller than these terms, but the series made of these terms converges. So what does the ordinary comparison test says? This summation b sub n must also converge. We couldn't do that to the original a sub n because a sub n could be negative. Ordinary comparison test requires our terms always to be non-negative. Okay, so therefore, by the ordinary comparison test, the series b sub n also converges. But once again, the series converges and the series with absolute value converges. So if we now subtract absolute value of a sub n from b sub n, that new series, summation bn minus absolute value of a sub n, must converge. Okay, if two series converge and you add or subtract them from each other, then the resulting series will also converge. Okay, however, who was b sub n again? It was simply a sub n plus absolute value of a sub n. So if we subtract absolute value of a sub n, then the two absolute values will cancel out and we simply get a sub n. All right, so therefore, This infinite series is simply summation of a sub n, and that is going to converge. All right, so we can now decide whether or not this infinite series converges. It's not always positive. It is not alternating either. Sometimes 3 in a row is going to be positive. Sometimes 3 or 4 in a row is going to be negative. So none of the tests that we have so far can be applied directly to this infinite series. But that last theorem allows us to skip the original series and try to attack the series with the absolute values. Okay, so when you simplify the absolute value here, in our examples, we had minus 1 to the n. That simply went away. Sine of n does not go away, okay, because it doesn't have to be 1. However, we do know that the absolute value of sine n is less than or equal to 1. Okay, so the terms of our series with absolute values is less than or equal to the terms of a convergent p-series, because 2 is bigger than 1. And therefore, according to the ordinary comparison test, our series with the absolute values converges. In other words, our original series is absolutely convergent, and according to the last theorem, if you pass the high bar that your series is absolutely convergent, then your original series also converges. Yay! All right, so we close section 2H by generalizing a couple of observations regarding geometric series and p-series. You can have a geometric series where r is negative, okay? But we know that if r is between negative 1 and 1, then the geometric series converges. And if r is bigger than 1, your geometric series diverges. So we can say that if r is less than 1 in absolute values, then your geometric series converges absolutely, because minus 2/3 to the n absolute value just becomes positive 2/3 to the n. And it doesn't matter if you have 2/3 to the n or negative 2/3 to the n. Both of those geometric series will converge. What did we see about alternating p-series in our 3 examples? So we saw that for harmonic series where p equals 1, it was conditionally convergent. And when p is 5/7, we got something which was also conditionally convergent. So that's going to happen because when you take the absolute value of this, you simply get 1/n to the p. And we know that the p-series converge when p is bigger than 1 and diverge when p is less than or equal to 1. So therefore, the alternating p-series absolutely converge if p is greater than 1, but are only conditionally convergent if p is less than or equal to 1, but still positive. Okay, so I said that we are going to cover parts of section 2I and 2J. So what are those about? We are going to see what are called rearrangements of infinite series. And what you can say, what we are going to change the order in which we are adding the terms of our infinite series. So let's go down to a definition which appears a lot in mathematics. It talks about a permutation. A permutation of a set A, and in this case, the set consists of the positive integers k, k plus 1, k plus 2, and so on, is a function with domain A and also range A, with the property that for every integer in A, there's exactly one integer j in A, so that sigma of j is I. So in other words, Sigma n from k to infinity, is a sequence made of the integers in A, but possibly in a different order. Okay, so that's why the term rearrangement is going to be useful. And every integer in A must appear exactly once. You should not exclude anybody. They should all be there, except possibly in a different order. Okay, so now let's apply this to an infinite series. A rearrangement of our infinite series, summation n equals k to infinity of a sub n, is another infinite series, summation n equals k to infinity b sub n, where b sub n is a sub sigma of n. So in other words, it is a series of the form where we use the original symbol, summation n equals k to infinity of a sub sigma n. Okay, so that's a lot to swallow in this definition. Let's go back to our workroom and see what happens when we arrange two of the examples that we saw. All right, so we saw these two alternating p-series, one with 7 over 5 and one with 5 over 7. The one with 7 over 5 is AC, absolutely convergent, but the one with 5 over 7 is only CC, conditionally convergent. All right, so here's what we're going to do. We are going to actually spell out what is happening, who are the terms of these two infinite series. Okay, so we start at 1, minus 1 to the 2, so we start at positive. 1 over 1 to the 7/5. So it's going to be just 1. But to start us off, I am going to still put that 1 here, even though we know it means 1. When n is 2, you're going to get minus 1 to the 3 minus. So it is alternating, of course. So this time it's minus 1 over 2 to the 7 over 5. And then at 3, it's going to be minus 1 to the 4, which is back to positive. Of course, it's alternating. So now it's going to be positive 3 to the 7 over 5. And then the next one will be minus 4 to the 7 over 5. So I'm going to be clever and just copy these two and turn this into a 3 and that into a 4. And once again, after 4 will be plus 5. So we will have 1 over 5 to 7 over 5 minus 6. 1 over 6 to the 7 over 5, and so on. Plus, minus, and so on. Plus, minus, blah, blah, blah. Okay. So, yeah, you know what? Yeah, let's do a couple more pairs. Yeah, might as well go all the way to 10. 5, and then let's go 5, 6. Let's go 7, 8, 9, and 10. 7, 8, 9, and 10. 5, 6, 7, 8, 9, and 10. Okay, so this goes on, of course, but we can approximate this infinite series using S10. Okay, we have 10 terms right there. Maple, it's about 0.733. Okay, so let's put that on the next slide. Okay, great. Let's do that also with our other series. Excuse me. Problem is I have two sliders on the right, one for the PDF and one for Scientific Notebook. And of course, I always click on the wrong one. Okay, so we're going to do the same thing with our conditionally convergent series. So we are going to start with positive 1 over 1 to the 5 over 7, and then minus 2 minus 1 over 2 to the power 5 over 7. So let me begin by just changing these exponents to 5 over 7. And then the next will be plus 3, 4. Okay, so it's exactly the same pattern here, but it's easier to change the base rather than the exponent, don't you think? Okay, there you go. 1, 2, 3, 4. Let me scoot over here. And then we want 5, 6, 7, 8, 9, 10. Up, up, up. Okay, 3, 4, 5. And then 6. And then 7. And then 8. 9. Isn't this fun? And 10. Okay. So what is this approximately? We get, something very small. 1.50 times, so 0.015, I believe. Okay, cool. So now, we were talking about rearrangement of an infinite series. I'm going to start rearranging the terms for, let's do the second one. Okay, so what does that mean? We are going to take all the terms in the infinite series and add them in a different order. And you might say, well, shouldn't we get the same answer? Because, when 2 plus 3 and 3 plus 2, they're exactly the same. All right, there's only one small problem. We're never going to run out of numbers. Okay, that's an infinite series, accent on infinite series. So how are we going to add these in a different order? Okay, here's what we're going to do. It's a simple rule. We will investigate what happens when we add the first two positive terms followed by the first negative term, then the next two positive terms followed by the next negative term, and so on. Okay? So in other words, think of it this way. We're going to give priority to the positive terms. We will let them in 2 at a time. But for every 2 of them, we're only going to allow 1 negative term to follow. Okay? So, the first 2 positive terms are 1 to the 5 over 7 and 1 over 3 to the 5 over 7. Okay, so those are the new first and second term. Okay, and yeah, if you're beginning to feel uncomfortable, I don't blame you. Yeah, this is weird, isn't it? So the first negative term is minus 1 over 2 to the 5 over 7. Okay, next triple. We have done 1 and 3, so next we have 5 and 7. Okay, so grab 1 over 5 and grab 1 over 7. Okay, and then the next negative term is the 4. Ooh. Okay. Next, I want to put 10 numbers here because, I want to compare apples to apples. All right, I have 10 terms here. I want to put together 10 terms, and right now I only have 6. Okay, but after 5 and 7, I need 9 and 11. 11 is not even on this partial sum, but that's okay. We're going to let 11 have priority. Ooh, isn't that special? But the next even number is 6, so that's minus 1 over 6. Okay, so right now we have 3, 6, 9 terms. Okay, so we want one more term after 11 is 13. So I need to add 1 over 13 to the 5 over 7. Okay, so now, maple, what are we going to get? 0.16. Where's the 10 to the minus 2? Oh, it's not there. It's just 0.16, period. Which is a lot bigger than this number. Okay. So, yeah, and of course, it's because we added up 10 different numbers than the ones that we have in this partial sum. Okay, so by the way, are you convinced that if we wait long enough, every number here will appear in the partial sum? You should be, because we have 1, 3, 5, 7, 9, 11. All the odd denominators are there. And then we have 2, 4, 6, 8, 10. Oh, we only have the 6 here. But if we wait one more round, 8 will be there. Okay? So even though we are having the odds, giving them priority, all the evens will still eventually be in the partial sums. You might just have to wait a lot longer. Okay, so, speaking of which, they're going to say, hey, wait a minute. Okay, what about us? Let us play. So, next, see what happens if we flip the priority. Okay, in other words, we're going to let 2 negatives in, followed by 1 positive. Okay, and they're like, yeah, it's our turn to be special. So minus, we got 2, we got 4, and then we have the plus 1. Okay, so after 2, 4, we have 6 and 8. Minus 6 and minus 48. After the 1, we have the 3. Ooh, my turn, my turn. After 8, ooh, we got the 10, and then once again, I am out of these numbers, but it's okay, I can make more. There's still 12. 1, 2, 3, 4, 5, 6, 7, 8. We need 2 more. So I need, after the 3, we want the 5. And then we want, so yeah, we want negative 14. After the 12 comes 14. Okay, so those are the 10 numbers that we would get if we let 2 negatives in, followed by the next positive. 2 negatives, positive. 2 negatives, positive. Next negative is 14. Okay, and again, if you wait long enough, everybody that is on the list over here will appear on the partial sum. Okay, so now, let me get out of the way here. What are we going to get when we get this partial sum? I'm sorry, 0.164, should I believe that? Oh, yeah, sure, because we have big one over here. So it's still not quite the same as what we have over here, okay? And definitely very different from this partial sum. Okay, so what is the point over here? What's happening? Well, it turns out that the rearrangements for a conditionally convergent series can be very, very different from the actual limit, the actual exact sum of the original series. We can already tell from here that we're going to get a very different answer from this, and this will also be a very different answer from this. And in fact, if you browse through section 2J, is it J? I believe so. You're going to find out that if you want any number, pick your favorite number, like pi. you can rearrange this conditionally convergent series so that its exact sum is going to be pi. It's bizarre. It's really weird. But that is one property of conditionally convergent series, which is not shared by absolutely convergent series. All right, so here is the first series, which is we said is absolutely convergent. So let's play the same game. So add the first two positives, followed by the first negative, then the next two positives, followed by the next negative, and so on. Okay, so the first two positives are, again, the 1, followed by the 3, and the first negative is the 2. And then after the 3, we have plus 5 and plus 7. After the 2 is the 4. After the 7 is the 9, and then we're out of this list. We need to manufacture 11. After minus 4, we have minus 6. And what do we have? 3, 4, 5, 6, 7, 8, 9. I need one more, so after 11, we are going to have 13. Okay, so this S10 gives us 0.733. How much are we going to get here? 0.89. Ooh, that's kind of big. Okay, I'm kind of worried a little bit about that. Okay, but that's fine. Let us add some more terms. Okay, so what if, so we're going to take that and we're going to add some more. Okay, so after, where are we? Minus, okay, plus, plus, minus, plus. We need another plus. So we need the 15 here. And then we need another minus. So the next minus will be 8. Okay, what do we have now? How much do we have now? We get, 0.85. So first it was 0.73 S10. And then we got a much bigger number, 0.89. 10 numbers, still 10 numbers, but we use some terms which were further to the right here. But now we doubled back and say, okay, let's let the 8 catch up. But we still have 13 and 15 who are further down. Okay, they're kind of running away, right? Okay, and instead of 8.9, we got 8.5. We got smaller. Okay, so you know what? Let me shrink the screen a little bit. Let's go 150. Okay, yes, we are gonna add a couple more terms. Okay, so where are we? I need 2 more pluses and a minus. So after 15, we need 17 and 19. And after 8, the next guy is 10. Okay, what are we going to get? 0.8535. Ooh, smaller. Ooh. Okay, so, oh, by the way, I mentioned apples and apples, right? So it's kind of unfair that we have 13 terms here and 16 terms here, but we're comparing it to S10. Okay, so it's saying, oh, wait a minute, you're not being fair. Compare this to, okay, how many do we have? 3, 6, 9, 12, 15 terms. So we're not adding to infinity, we're only adding 15. Okay, and what do we get? Pray tell, what do we get? We get 0.76. Okay, so it's a little bigger than 0.733, but still not quite the same. Okay, shall we do one more round? Copy this. Okay, scoot out of the way. Next, what do we have? After 19, we have 21 and 23. And after 10, we have 12. Ooh. How much do we get? 0.84. Ooh. Still, it's a little bit smaller. Okay, so let's see. Let me see if I can fix that. That's better. Okay, so now let's compare to what happens if we have 18 terms. Okay, because we had 15, now we have 18. So let's take this, compare this to summation n equals 1 to 18, regular partial sum. We're gonna get 0.74. Okay. So obviously we can keep going like this, and it is a little tedious adding more terms, 2 positive, 1 next negative, and so on. So in section 2i, we actually prove that no matter how you rearrange the terms of an absolutely convergent series, you are always going to get the same exact sum. It's the exact opposite of what happens to a conditionally convergent series, where you can pick your favorite real number. It could be positive, it could be negative. And you can make a rearrangement of that conditionally convergent series whose exact sum will be that favorite number of yours. It's simply bizarre. Okay, so on that note, we can now see why absolutely convergent series are, in a sense, far better than conditionally convergent series, because you really want only one exact sum for an infinite series. You don't want an infinite number of possibilities. That doesn't make for good math. Okay? All right. So on that note, we are again just shy of an hour. I hope you enjoyed this video. And in the next couple of videos, we're going to finish off the tests for convergence or divergence. Namely, we will look at the ratio test and the root test. So until then, I hope you enjoy the rest of your day. Bye.